Hello, everyone. It's a pleasure to be back in my alma mater where I spent a decade and to see so many good friends, former faculty, and PhD advisors in the audience. It's crazy that it took a decade to come back to MIT and speak after my thesis defense, but here I am. So thank you to Babret and Munzer and everyone else for the invitation. I manage the core data science team at Facebook. Facebook's mission is to connect the world and help build a community. And we have a number of teams at Facebook that do different kinds of research. We do research in a number of different areas. Oh, it's not working. Pointer's working. Sorry, I can't. Oh, that's a button. Nice. Thank you. There we go. So we do research in a number of areas. Facebook, I mean, there's many different teams. You probably have heard of at least a couple of teams that do machine learning related research. There's the applied machine learning team, Facebook AI. I'm going to be talking mostly about some of the work that the data science team has been doing. That's the one I manage. We have about 80 PhDs in the team. And it's a good mix of people who do statistics, computer science, and all the usual suspects, in addition to social sciences. We have political scientists, sociologists, economists, and so on. So it's pretty diverse. And that makes it challenging to represent their work well. So instead, I chose two areas of active work that I'll talk about, but they're just examples, and there's many others that are pretty different. Overall, the range of projects include descriptive analysis to better understand how people interact with each other on Facebook, how they interact with our products, how that impacts individuals and society. We also develop some signals that are consumed by many algorithms within Facebook in the various products. In some cases, we design the algorithms themselves, auctions, marketplaces, and whatnot. So our work is really significantly varied. Safety Check is one of the products that I'm the proudest of at Facebook. It allows people to mark themselves safe and let their friends and family know that they are safe after an attack or a natural disaster. And one of the scientists in the team, her name is Paige Mass, you'll see a picture of her shortly, had the idea that information related to Safety Check could be helpful for humanitarian organizations as they're planning responses after a natural disaster, such as a fire, earthquake, and whatnot. So we've seen more and more organizations like the UN in this case acknowledge the role of data and technology and help them plan responses. And because of that, Paige started to engage with a number of organizations, NGOs, to figure out what kind of information would be helpful and getting it to them at the right time so that we can actually impact how they deploy relief while obviously preserving privacy. So at that point, we figured out that they had a number of key questions. Where are the people affected? Where are they safe? How is that changing over time? Are people moving? And so on. And obviously, things change in space and time. And unless you have clean data to provide, and in a timely fashion, it's not particularly helpful. So after that, we thought about the data we had. And one of the most important ones is location data. About 15% of Facebook users have location tracking enabled. So we get their coordinates over time. And we decided let's use those in an aggregated fashion to see to what extent we can understand what happens to society after a natural disaster. The methodology is very simple, actually, at a high level. We grab a map, we break it into tiles, and then we compute some statistics per tile. We throw away tiles that don't have enough data, and then we display them in maps. And in many cases, we actually pass on the data to the organizations, and they have their own maps, and they just layer our data on top of those maps. So at this point, we decided to go back in time and figure out if we can see useful patterns in previous disasters. Let's see. We started by looking at Typhoon Damrey in Vietnam, and we produced this map that shows, I guess you can see here, but basically per tile, we look at how many people are present. Then we compute a simple z-score per tile by looking at the statistics at the mean and the standard deviation of all the squares in the map. And then we're plotting here in blue areas where there's more people than the average, and in red areas where there are less people than the average. And what you should see is that along the coast, you have some areas that are a little bit blue and some areas that are red. And then inland, of course, you have much more blue. Oh, that didn't work. Sorry. Somehow, this was a simulation, or showed 3 different pictures. And what you saw is that all the blue here, after the typhoon hit, moves inland. And all of this becomes heavily red. And then you see a lot more blue here. So that was a good sanity check. I'm sorry that that doesn't show. I think I should have sent the PowerPoint, not the PDF. We also went back and looked at wildfires in Canada. And at this point, we decided to look at, per area, the percentage of people who had marked themselves safe. And then we compare that against news. And we felt very good about the correlation we were seeing between news reports of what was the situation on the ground and the data we were seeing. But again, at this point, we hadn't benefited anyone. We were just looking at what could we have found had we looked at our data in time. So to move this into the field and actually make it useful, we started in Hurricane Harvey. It arrived in Texas, and at this point, this was the first time when we tried to compute movement, where we literally took the delta of people that left a particular tile and showed up in another tile. And what you can see is that initially, you have a bunch of bright lines from Corpus Christi to San Antonio, for example, Austin, Dallas, and Houston. And that means that you have a bunch of people moving from Corpus Christi to San Antonio. And then as the disaster got nearer, you can see that most people have already left Corpus Christi and have gone to Houston and San Antonio. And then you can see that people continued on to Dallas, not San Antonio. So San Antonio is not that bright anymore. And then when disaster actually struck, most people just stayed in place, and you saw very little movement in the cities. We were working with the Red Cross, and they were already planning a response. And they were wondering whether to set up shelters and what resources to send in San Antonio and Dallas. And they didn't know how many people to expect in each of the 2 cities. So we were in contact with their data scientist at the same time as this was going on. And it was actually them who built the maps that you're saying we passed on the data. We saw that more people went to Dallas, which was a surprise to them. They had actually sent more resources to San Antonio. And then based on our data and their own data, they ended up having to change the strategy. But in a sense, it was already too late. They had already paid the cost. But that gave them enough information to decide to, I guess, loop us in earlier, the next opportunity. And indeed, for our next hurricane, I think it was Hurricane Irma, we moved to getting a map in time to them for their National Response Center. But they still didn't actually use it. It just meant that more people who could actually use the information saw it and got exposed to that. And it was only until Hurricane Maria in Puerto Rico that we finally were able to use this data or pass data in a timely fashion that they were able to use to plan a response. And in particular here, the Red Cross used their data to generate maps of connectivity in the island. And they used that data to decide where to send trucks daily that could provide connectivity to people in Puerto Rico. What this map shows is that around San Juan, that's where you see all the blue, the infrastructure was more resilient and people were still relatively connected to the internet, but pretty much in the rest of the island, the connectivity was gone, as is of course widely known. The Red Cross was very happy with this, so they wrote a blog post, and if you look at it, they basically are asking more companies and more people to provide data because it's extremely useful to them. So that was very good to see. At the same time, we were working with the World Food Program, also for the same hurricane in Puerto Rico, and they were interested in the same question, also addressing connectivity issues. So for them, we came up with another slightly different approach, but ultimately that showed the before and after of connectivity, since we have temporal data as well. On the left, you can see the map of relative connectivity in the entire island. So here, red is high, blue is low. So you see that around all the major cities, there's good connectivity. And after the hurricane, you can see that the map is mostly black because people have just mostly completely lost connectivity. Now we're working with several other organizations to help them assess the state of roads and bridges to be able to better plan the routes that they should take as they try to deliver aid. Again, Paige was the main scientist in the team involved in this, but there were many people from multiple teams at Facebook and, of course, in NGOs who have been involved and continue to be involved with this work. So that's project number 1. Switching gears, I thought I would feel too dirty coming to MIT and not show any equations, so I have a few more equations just at the end. So the second topic has to do with what we call variant testing and applying a generalized form of Bayesian optimization for this. This is the work of Eitan Bakshi and his team. And in fact, I think Ben is also another PhD from MIT in optimization. All right, so variant testing, you probably already know what it is. Some other companies call it A/B testing or experimentation. You want to figure out what's the best version of your product to show to people. In this example, we're trying to get higher participation rates on a survey. And you can imagine changing either the text or the logo and so on. So you can write software to implement many different ideas and then deploy different variants to different people and then see what percentage of the people that see each experience choose to participate in the survey and give us data that's useful. So maybe the text is not enough, so you can come up with some cute icons to replace the burning like hand. Then you, again, deploy it. You measure the results. You get confidence intervals. And you can rank the different variants that you track based on the effectiveness, in this case, the participation rate. And what you often see when you A/B test is that typically the default version that, say, product people, designers, or the entire team guesses might be the best one is very often not even in the median. And you find a surprise. I think in this case, it was the fox icon that did much better by far. So just pretty funny. So in addition to A/B testing discrete experiences, like again, in this case, 48 specific options. In many cases, what you want to do is optimize the parameters of a machine learning model, whether you're using the model for maybe managing how to scale up or scale down a bunch of computers, maybe to tune a ranking function for main product at Facebook or whatever it is. And the point is that these evaluations are extremely expensive and the results are noisy. And the parameters are often continuous, not discrete. So you're not testing discrete arms, but you need to find the best parameters or good parameters from a continuous space. That's the problem that I want to talk about. And that's where we use Bayesian optimization. At a high level, the idea is we have this function we want to optimize. We want to find the parameters that optimize that. But again, the function evaluations are expensive and they're noisy. So what we try to do is fit a model. We fit a model using Gaussian processes and Gaussian process regression, and then come up with a function that tells us which sets of parameters to evaluate next, either in batch or just completely in series. And then we repeat until we feel like we've climbed the gradient enough, or we run out of time or something. So here's a pictorial way to show the approach. So imagine that, again, we want to optimize some metric, and imagine that the true dependence of that metric f on some parameter x follows a gray curve in the background. And we've already had 5 measurements. That's where you see the x's and the error bar, so they're noisy measurements. So what we do is we fit a Gaussian process, and then what we're showing here in blue is the mean of the posterior of that estimate, and then the uncertainty bands that the model provides. All right, so in this case, imagine that the challenge is to find the parameter that you want to explore next, because on the one hand, you can just exploit, so to speak, and choose maybe the value of x that maximizes the mean, but then you don't learn very much, and you may miss out, for example, on some parameter values close to the right, where the uncertainty is high. So it may make sense to actually evaluate some parameters there to reduce the uncertainty of that part of the space. So the second stage is coming up with this acquisition function, which in Bayesian optimization, it is the expected improvement. And it is the average over the posterior of your function of the potential improvement you would see at point x relative to the best known value of the function. So if you can evaluate this function easily, the expected improvement at multiple values of x, then you could choose the x that maximizes that function as your next evaluation. So when you do that, you'd end up with a value that maps to the purple line that you see there. So let's say that we indeed evaluate that. So now you get one more data point here, and you update the Gaussian process regression. You repeat, you recalculate the expected improvement. Now it looks like this. You find the maximum value of x. It's this one. So you run an evaluation there. And you continue again repeating. So that was vanilla Bayesian optimization, basically. But again, one issue for applying that to our real world of variant testing, where all evaluations are very noisy, is that it doesn't behave well in the presence of noise. Essentially, you need to assume that at the points x where you evaluate the function, there is no noise. So effectively, the variance is 0. And it's not that Gaussian processes cannot handle that. They do. The issue is the interaction with the acquisition function. Now you don't know the best value of f that you've observed so far because all of your observations have been noisy. So for example, it may actually pay off to go back and reevaluate f at the same value as you've had before if it looks good enough on average and the uncertainty is high enough too. There are several approaches that have attempted to deal with this. For example, a commonly used one is to look at the mean as a function of x of the posterior and then find the optimal value of that mean and then replace the optimal f so far by that quantity. But you can show that if you do that, in many cases you end up over-exploiting and clustering evaluations, future evaluations, around previous measurements if the noise is too high. Now, in addition to that, typically we need to optimize functions with constraints. So for example, let's say we're trying to improve the experience of watching videos or seeing images by using different, say, compression techniques or policies to determine what bitrate to use as a function of time. But we also don't want to increase data usage by too much. So there, the increase in data usage could be a constraint. And again, typically in these setups, the constraints are also noisy. You cannot observe them exactly. You don't know if a particular value of x that you've sampled is even feasible. You don't really know if it actually mostly respects the constraints that you want to keep. So the team has been working on a number of generalizations around Bayesian optimization to make them work well for variant testing in these kinds of setups. And they've also built a tool that allows anyone at Facebook to apply these methods to a wide range of problems. Most of them are indeed variant testing, but others even involve offline but very expensive evaluations that don't have anything to do with users interacting with the products. In this particular paper, they focused on developing a way to allow for a reasonable method in the presence of noise in the observations and noise in the constraints. Let's see. Oh, and they took a hint from another approach that allows one to come up not with one parameter value to evaluate next, but with a batch. So in this case, imagine that we pick these 5 values where the purple lines are in one go. And that's because in many cases, you can actually run parallel experiments, parallel A/B tests, parallel variants at the same time. And in this approach, what they did is, let's see, hold on. I don't have it. Let's see. What they do is basically think of serially, let's say that we had found that this would be the next point to evaluate. But before waiting on the result of the evaluation and refitting the model and so on, we simply include the outcome of that new measurement as a random variable and then integrate it out in the acquisition function. And then using that new function, even though it doesn't have an analytical solution now, you can evaluate it numerically, for example, using Monte Carlo techniques. And then you can repeat to obtain the second point, the third, and however many you need. And then you run that. So they liked that idea, and they thought about it, and they realized that it would apply equally well to the problems they were trying to solve. So at a high level, that is indeed what we do. So I have a quick summary so that you get a feel for the math. This is, again, the vanilla version before their generalization. You're trying to maximize a function subject to some constraints. We have this acquisition function that's alpha EI for expected improvement. In the presence of constraints, you need to modify it and extend it here with the product of the probability of satisfying a constraint at a given value of x. And that is because, I guess I haven't said this very well, for every constraint, j, you also learn Gaussian regression and you have a posterior. So again, in the vanilla application, at the points x where you have evaluated things in the past, you know exactly the value of each constraint and exactly the value of each function. But once you deviate from those x's you have measured, the Gaussian process provides a confidence interval. So that's why you need to assess the probability of actually satisfying the constraints or each constraint at a particular point x. And when you want to obtain multiple points, then instead of having the best known value so far, if you want to do a batch optimization, then again you add other random variables that have to do with the current values you're evaluating, and then you just take the expectation over them and optimize that resulting function. So what they do is basically generalize the acquisition function, but using the same idea. So we now have a posterior distribution over all the batch measurements we want to make, and also over the previous measurements we have made and where we have gotten results because there's always noise present. So now, basically, every point in the space has some non-zero variance. And in addition to that, we also add the value of the constraints, also each based on a Gaussian on a Gaussian process posterior, and then we integrate the two out. So we integrate all the random variables out. Again, the solution is not analytical, so we use quasi-Monte Carlo techniques to evaluate that at different points x, and then we get whatever we want, either batch values to evaluate next or the next best value to test out. The plot shows one application of it to a real system at Facebook, a pretty large-scale system. It shows in Y the objective metric we were trying to maximize in this case. And then in the x-axis, the constraint. So we did not want to decrease a particular thing by more than some amount. That's been normalized here. We're showing a combination of hand-tuning, random values, and then a handful of evaluations that were obtained using this methodology. And what we observed is that after very few attempts, the 3 in blue, we were able to find a much better version that was both feasible and that did better in terms of optimizing the main metric we cared about relative to the other approaches. So it works very well in practice, and again, at least within Facebook, it is widely used. All right, this is the team that's been working on this. With that, I'm happy to take questions on either of the two or on anything else. Thank you. I think I know you. Leonid is one of my PhD advisors.
All right. Carlos, fantastic talk. On the Bayesian optimization, usually the setup is such that you do kind of a random exploration of the space, and you're trying to minimize the cost for the next move and make the most informative move. In your case, you have huge distributed resources. So instead of making one move in a particular direction, you can make simultaneously 10,000 measurements.
Maybe not so many, but yes.
Okay, okay, fine. So you can do lots of things simultaneously. You would get fewer statistics from each. So you would have high uncertainty, but you can do them, but you save time. So have you considered strategies when instead of doing a path, you do like a branching kind of exploration at a higher variance, but fast?
We haven't. I have asked the team about that, and in particular about looking at, for example, user-level outcomes and modeling things at that level instead of looking at the aggregate results across a population. I think it's mostly lack of time so far that we haven't gotten to it, so we don't know. So for example, another idea that I would love to explore is not relying on Gaussian process, but instead doing something as simple as a second-order approximation, even if it's locally, and then optimizing locally and continuing that on. We haven't tried that. This team is, I think, in love with Gaussian processes. They know how to use that well, so they've been focused on finding ways to solve more problems using that. So for example, one thing they are working on now is combining the results of offline and online simulations and learning the mapping at the same time as you learn the rest of the model, so that you can use that information from the offline simulations to better predict or reduce the variance of your online outcomes.
Hi, I had a question. So my question was regarding your first presentation.
Sorry, who's speaking? I can't.
Yeah,
oh, thank you. Hey.
Hi. So I had a question regarding your first presentation.
Sure.
Which was that, so you're making these like very mission-critical resource allocations based on like crowdsourced data. So with something like Netflix, that makes sense because there's no externalities. But here, am I not incentivized to just say I'm not safe so that more resources get poured into my neighborhood than someone else's? Like, don't you think that will be an issue if more and more, like,
I mean, I suppose if you manage to organize enough people to do that, then I suppose things could be...
Every individual person could do that by themselves.
No, I think you need too many people to do that for it to actually affect the outcome. But, I mean, theoretically, it's certainly possible. The main thing, though, is that the inspiration was safety check and the safety data, whether people are marking themselves safe or not. But ultimately, what we have found most helpful is assessing movement and location and population density. And I think that's harder to change. I suppose you could artificially disconnect your device from the internet so that we think that now you're not there. And that could throw things off, I suppose.
Hi, Carlos. Thanks for the
Hi.
talk.
Sure.
Question about the Bayesian optimization.
Yes.
So whenever I hear these super nice techniques for basically taking field experiments to a whole different level,
Yeah.
I'm very excited. And typically the methods are coming out of the online world from Facebook, Google, online companies that are like heavily invested in developing these methods. I'm very curious to know and would be very excited to think that it's possible to take this out of the online world into the offline world. For instance, if you think about
Yes.
policy, there has been a big movement in the past decades on policy evaluation with randomized experiments. However, what you're doing here is basically policy design, not policy evaluation, which is, I think, super interesting. You could think of even like designing drugs with this type of framework, or simply social policies with a framework not on policy evaluation, but policy design. So my question to you is, how much N do you need for these methods to be to have basically an edge and to work? Because typically, I think the main difference is that online you have perhaps millions of N of experiments, but maybe on the offline world you would have thousands. So would you see the value of this type of things on the offline world as well?
We do. So far, most of the applications we see have a handful of parameters, from what I understand, say on the order of 10. Many teams have found pretty significant gains using this technique, even when they only have, say, 20 previous evaluations to come up with the next ones. So think about the alternative. And the alternative is what say, my team has been doing forever, not only at Facebook, but also at Netflix and at Google before, which is you have a bunch of researchers and engineers carefully looking at, say, search queries for Google or video recommendations for Netflix, ranking outputs for Facebook, and then trying to come up with a hypothesis of what's going on and how to achieve a different behavior, and then using some intuition to come up with the next set of parameters to evaluate. And once that happens, then you wait. You wait a week, 2, in the case of Netflix, 2 or 3 months, to get the result and then potentially iterate. So it's that hand tuning that it's incredibly slow that this is trying to significantly speed up. And again, because of that, even though we have maybe a large N, in many cases you still need to go through a sequence of evaluations, and you don't have too many. So it's on the order of 10 or 20, and then you're already in business.
Okay, thanks.
Good question, thank you. Sorry, one more comment. You talked about the offline world, and again, we do have some applications that have nothing to do with variant testing on users, and that instead are basically doing hyperparameter search. So maybe even in the application of the kind that Bean was talking about, if you have very large data sets and it's just very expensive to come up with an evaluation, this method, of course, still works.
You mentioned that security and privacy were one of the areas that your team works in, or your department works in. I'm wondering what sort of efforts or insight you have in that area that would identify and mediate or prevent the kind of data exposures that have made such big news in the last couple of months for Facebook. I mean, in particular, I'm asking, do you have insights in how to improve your customer, your users' confidence that they are not being unfairly or unreasonably exposed, assuring them better?
Yeah, my team does not work on that. But for every project that anyone at Facebook works on, we have to get it reviewed to make sure that it respects privacy and whatnot. So what I meant to say is that in the case of disaster maps, we only provide aggregated enough information, and if it's not aggregated enough, we just drop it and don't pass any data for that particular tile to respect privacy and so on. But in terms of the recent news and any efforts related to that, because I don't work on the team responsible for it, I think any comment I make could only add noise, and it's probably more accurate to go to the source of truth, which is the newsroom and
I wasn't
those
asking
materials.
for insight into what
Yeah.
Facebook is implementing.
We don't do any research on
you
privacy.
Don't do any
My team
research
doesn't do any research on privacy.
Okay, on privacy.
We just go through the
On
privacy
how to
processes for
how
every
to
project we work on.
effectively do it and guide the rest of the company.
Yeah.
Don't do that. Thank you.
We do some research on algorithm fairness and so on, but maybe we can chat offline. Sure. I think that guy with a beard has a question.
Well, thank you for putting me on the spot, Carlos. Well, I guess my question would be on, you know, this idea on the relief maps. You know, I thought that was a pretty neat use, you know, of real-time data. From the other projects that you're working in, what other applications on the, you know, data for good? Can you give us a couple more examples of what other projects that you didn't have time to talk about in the similar vein?
Yeah. We have a product, Facebook, not my team. Facebook has a product trying to create more efficient markets for blood donation. So far, they're in India and in a handful of other countries. It's very early on, but it's, I think, a pretty cool project. They're also creating, so we have a team that's called the Social Good team at Facebook that owns multiple products and is developing other new ones. They're also developing a product to enable people from all over the place to find long-term mentors and to somehow help the mentors facilitate teaching the mentee a number of things over time. There's a few other ideas too, but those are the main ones that are already in production, so to speak.
So recently, you know, I came in very, very late into social media, and I've been using Twitter, for example, a lot for science, and, you know, for pretty much, you know, maybe broadcasting, you know, some of the things regarding papers and outcomes, you know, in from my research group and whatnot. Does Facebook have any plans on how to connect scientists better in
Not
terms
that I
of
know
the
but
academic
I
world?
wouldn't know. It's such a large company that I've never heard of any such plans, but that doesn't mean there aren't any. Sorry. Thank you.